such opportunity. So, okay, let me start. So this, so today, so as he told, I'll give two talks. One is today, and the other is the day after tomorrow. And these two topics are different, so not related. So today the title is Mapping a Knot by a Continuous Map. So you see, this is my family name, Taniyama. Tani means valley, and Yama means mountain. So this is my logo mark. And this is my first name, Kouki. And from Waseda University, Tokyo, Japan. Okay. So, okay. And so, so today's talk, I consider the following content just by accident. So, okay. Anyway, let me start. So, suppose we have a transparent paper, and on which a right circle is drawn, something like this, and fold the paper along this dotted line. Then we see, since these papers are transparent, we see this part and this part simultaneously. Then this image of this right circle is no longer a right circle, but still topologically a circle. Okay, so then how about this phenomenon in one dimension up? So suppose we have we are living in 4-dimensional space, and draw a knot in a transparent 3D paper. So this is a paper, 3-dimensional, and drawn a knot like this, and fold the paper. Since we are living in 4 space, so this lower part goes to upper part. So reflection by, suppose this is XY plane. So then this part goes to something like this. So we have this, so this image of this knot. So you can see, so this part can be moved to here by so-called Reidemeister move to, and this here. So you can see, if you are familiar to knot theory, then you can see this is a knot. So this is a tripod. So we'd like to generalize this phenomenon. So let me give some definitions. By script K, we denote the set of all oriented knot types in R3, and thus, so K, an element of script K is the oriented knot type, and then an element of this capital K, small k, is representative. You know that knot type is a knot type is an equivalence class of all ambient isotopic knots. So an element. So by this we mean this is a particular representative. So this is anyway a subset of R3 that is a circle that is abstractly homeomorphic to a circle. So today all knots are oriented, but I don't mention orientation so explicitly later. So then let this F represent holding. Anyway, let F be a continuous map from R3 to R3 defined by this formula. So X and Y are identical, and Z goes to the absolute value of Z. So you see this we can imagine this is X Y plane, and this is Z direction. Then so this part is identical, but this part goes to upper like this. So since we take the absolute value, so this thus we have this this map is modeled by this F. Then we have the following theorem. So for any knot types K and J, any two oriented knot types, there exists a representative, particular representative K representing capital K, such that the image, so you see this has some orientation, so the image carries that orientation. So this is also this may be a knot, maybe a singular knot, but this if it may be still a knot, non-singular knot. So this says that Fk is still a knot, non-singular knot, and that represents the knot type J. Okay, so the following is proof. The proof is in some sense very simple. So this this is proof by example. So for example, take K to be the right-handed torfold knot type, and take J to be the figure-eight knot type, and simply take a diagram of that is a connected sum of these two knots. But you see, so this is this not a figure-eight knot. So the crossing change to be, so this part is trivial. So we see this this knot is K trifold equivalent, and so put this knot slightly above the XY plane, but for these two part, so this underarc is go to below the XY plane, so like this. Then if we take F, so this under part goes to jumps, and then the result we have a crossing change. So you see this underarc goes to above like this, and this underarc goes to up to above xy plane. So after all, we see if we map this knot by F, the image is crossing change occurs. So you see this toroid is unknotted, and we now have the figured knot. So like this, in any case, so we may need some more crossing if K and J has high unknotting number. But anyway, so this construction shows the previous theorem. So I see, I say that this, we now prove this theorem. Okay. So in such a way, today I'd like to observe the knot types before and after mapping the knot by a continuous map. So usually knot is considered up to orientation preserving homeomorphism of the 3 space R3. But today, so this match. But today we consider continuous map of over R3 means continuous map from R3 to R3, R3 to R3. So this is usually mismatch. I think considered mismatch. So in particular, if this map not necessarily a homeomorphism or also not injective. So if the map is injective, it's not type is preserved or got mirror image. But anyway, so today we consider non-injective continuous map from R3 to R3. So this is mismatch, but today I consider this mismatch problem, and I don't know whether or not this study has any meaning, but at least I think some results are interesting. Okay, so this we need okay, for generalization we need this lemma. So I call this Terasaka-Suzuki lemma. So this says for any two knot types K and J, so there exists a representative small k representing capital K and small j of capital J that differs like this. So this is some tangle of many strings. So these two parts are identical, and only the difference is outside of tangle like this. So this may be some number of strings. Actually, we can take this to be the Gordian distance, the number of crossing changes needed to necessary to deform K to J. So today I don't show how to prove this, but it is a known fact in knot theory. So then this is a generalization of the previous theorem. So let F be a continuous map from R3 to R3 with some conditions. That condition is so this is just for simplicity drawn by figure. So there exists some 3 ball and a simple arc like this. Like this means this is annotated. Or this is ambient-specific to this figure, and that is mapped by F. So like this way. So this is not it's dotted right, but it's this ball pair is trivial, and this also outer tangle is trivial. So roughly speaking, the image is ambient-specific to exactly this figure. So if for F there are some such local part, we can have the same result for that says for any 2 knot types the same statement. There are some k that after mapping by F represents J. So the proof is easy if we use this lemma. So take for this 3 ball, take k. So this is 3 ball and maps to after mapping F. This part goes to this. So like this. Then we can show this theorem. And I show one other example of a continuous map. Let W. Now W represent the winding map, or this is a map defined by R. The W maps R sine theta, R cosine theta, and Z to be R sine 2 theta and R cosine 2 theta and Z. So Z part is identical, and so this is the twofold branched covering projection, branch along the Z axis. So you can see. So these two are polar coordinate. So if we this is trefoil knot and mapping. So you can see this. If we take this 3 ball as this and take this string as this, then we see the result goes something like this. So since this is winding twice, so this is about 180 degree and goes to 360 degree. So like this. Then we see this this part makes figure-8 knot, and this part makes knots. You can we can move this to this, and we can see this part is now annotated. So anyway, this is a trefoil and this is a figure-8 knot. Okay. Now I goes to another section. So from now on, we consider the following problem. So namely, we map a fixed knot repeatedly by a continuous map. So repeatedly means a continuous map from R3 to R3. So then repeats this map. So let me show first this folding map. If we map the twice of F, I mean, so this F2 means the composition of F and F. Then goes to, since F of xyz is xy absolute value of z, the twice of absolute value of z is equal to the absolute value of z. So we see the f of this is the same. So we have twice composition of f and f. F2 is equal and F3 all the same. So for this F, the repeat F2 is the same. So so in other words, the discrete dynamical system of generated by F is trivial. So this is not interesting. But we see for the winding map W, for example, we have the following example. So take a standard torus and take a standard right torus knot of type 1,3. So this is a trivial knot. But if we map this by W, so this winding twice, we have the torus knot of type 2,3. So this is a torofoil knot. And if we map this again by W, then we have torus knot of type 4,3. And so on, H3 and so on. So we see if we take this red line K, then WK and W twice K and W triple K all produce different knots. So we have infinitely many different knots simply by repeatedly mapping by W. So, okay, now I generalize this example. So suppose let n denotes the set of all natural numbers, and suppose we have any map from n to the knot types. In other words, suppose we are given any infinite sequence of oriented knot types. So for any given infinite sequence of oriented knot types, so there exists a representative K. So K is a subset of R3 representing the first knot type phi1, and exists a particular continuous map F of R3 such that if we map K by F, then the knot type is phi2. And if we map Fk by F, the knot type is phi3, and so on. So infinitely many possibly different, maybe the same sequence of orient knots we have by mapping K repeatedly by F. So how to prove this? And for the purpose, I prepare the following technique. So this is a local crossing change. So I mean, so by a continuous map of R3, that is identity outside a small three ball. We can change a crossing. So this this is a disk cross I, and this over arc is just on the face, top face, and so this under arc is just not the bottom face, but the middle of this disk cross I, the interior, and so this we have a map like this. So this is a cross section of this three space, and take so this dot means this dot means this arc. So this the arc is perpendicular to this point, and this line is this under arc. And for the explanation, we divide anyway. So divide this by this red part is actually solid torus. So go around like this, and two truncated cones, one and map this goes to this, and this goes to this, and this truncated cone is reflected by this face. So this is not of course this is not injective, 2 to 1, at most 2 to 1 mapping. So anyway, we can by a continuous map locally change a crossing. Then it is easy to okay, now I explain how to construct F. So take an infinite sequence of small three balls that is with these are same distances. Put infinite many three balls, and F is essentially except inside these three balls, F is just a translation by this distance. And for inside of this three ball, this three ball maps to this three ball, but some local crossing change occurs, so that this first knot type is crossing change to the second knot type. And for this three ball, F is defined to be such that this second knot type is crossing change to the third knot type, and so on. So anyway, in such a way, F is defined. F can be defined as a continuous map from R3 to R3. Then F satisfies this property. But I think this is So this theorem is not so interesting because for k is given and we can choose f after k. So then oh, I'm sorry. So this this is just a misprint. Oh, so this okay. No misprint. Oh, it's okay. So now I consider first fix a continuous map and then take various nodes. So so today I consider a tent map, so-called tent map. That is a famous example in the theory of discrete dynamical systems. Usually, maybe most famous tent map is a map from the unity interval 0,1 to 0,1, and the graph is this, so like this. But today sometimes tent map is considered with some parameter, and today I consider the tent map. So tent map is usually 0,1 to 0,1, but today R to R, and so some generalization. Anyway, for simplicity today, by tent map we mean exactly this map T. So that maps each real real number x to 3x if x is less than or equal to 1/2, and maps to -3x plus 3 if x is greater than or equal to 1/2. So let me show. So this is a graph of tent map T. So so for this this is 1/2, and it maps to 3/2, and so these are linear, and also this part are linear, and by using this is a map from R to R, and then I define a map capital T that is from R3 to R3. So for simply by first x, y, and y are identical, and the last z to tz. So the height is mapped by this tent map. And first, for simplicity, I consider this map, and iteration of repeatedly map T. Anyway, so first I review some okay. First I show I explain the result. So for this T, we have the following. So let K be any oriented polygonal node. So polygonal means K is a union of finitely many straight line segments. Then there exists and suppose that for any n natural number n, the K mapped by the nth iteration of T is still a non-singular node. So all T and K is still an oriented, and as a result is oriented polygonal node. Then we have there is some finite subset of node types such that every T and K belongs to this finite subset. So this is because so since this T is identical for X and Y, so if we have some polygonal node in R3 and map that node by T, these two nodes have the same XY projection. So only this part, the height is different. So if we have a polygonal node, then any node obtained from that node by the repeatedly applying T has the same XY projections. So by roughly speaking, only the difference is over and under of crossings. So in such a way, we can show that only finite set of node type appears by any repetition of T. Okay, the following is I think this the following theorem will be a bit interesting. So this let F be. So after this proportion, we should we cannot expect infinite many node types, but so we restrict some. We have some for any given finite subset of. So F is a finite collection of node types, and for any such collection and any sequence of so any map phi p to n to F, so meaning that means any finite any infinite sequence of node types, but these node types are all in F. So any infinite sequence of such node types, there exists a particular representative K of oriented. This K can be taken as a polygonal node. Exists small k such that if the node type of K is phi 1, so n is 1 is if n is 1, n minus 1 is 0, and T0 K means K, and so K is phi 1 and TK is phi 2, and t twice k is phi 3, and so on. So any requested phi infinite sequence of knots, but they are all contained in some finite subset. It can be realized by some k. So okay, let me show how to prove this theorem. So first I review known properties of this tent map. So tent map is this is a graph of tent map. So remember tent map. So now I consider T is a map from R to R. So this is just a one-dimensional story. So if suppose that a real number x is a minus, I mean is less than 0, then if we map x by t, then x goes to 3x. So it's more smaller number. So if x is minus, then by repetition, by iteration, x goes to minus infinity. So you know this. So this is a line of y equal to x. So this x goes to tx, and tx goes to t twice x, and so on. And if we have x is greater than 1, so then by mapping tx is you see minus, then t twice x is more smaller, and it goes to minus infinity. So I'm now explaining this part. If x is sorry. So okay, let me continue. So if we have a number that is between 1/3 and 2/3, so this is between this, then by tx is greater than 1. So this is level 1. Then t twice x is goes to a minus number, minus, and then goes to minus infinity. So if it is greater than 1/3 and less than 2/3, x goes to minus infinity by the repetition of t. And if we have an x that is between these, I mean greater than 1/9 and less than 2/9, then if we map x, tx is between here. And if we have this, so you know this this t maps this interval of length 1/3. From 2/3 to 1 is 2/3 is mapped to 1, and 1 is mapped to 0. So this interval is mapped to 0, 1. So you can we can imagine as you know tent map. So this tent map just this is R, and so just fold at 2 to 1. So goes to and extend this by so this is 0 and so 0 and the length is extend to triple. So anyway, then we see this from 2/3 and 1 is mapped to 0 to 1. So this if we have this from this point is 7/9 to 8/9 is mapped to 2/3 and 1/3. So this Tx is here and T twice x is greater than 1 and T triple x is minus. And thus we have, so this is the famous Cantor middle subset. So the take A1, A2, A3 like this, and this is intersection. And then it is we can see easily. This is well known by discrete dynamical systems that if x is in the Cantor middle subset, Tx is still in Cantor middle set, and vice versa. And if x is not in Cantor middle subset, then it goes to minus infinity if n goes to infinity. By repeated apply of t, x goes to minus infinity. So today, so we are interested in that x that is in the Cantor set. So I mean, x is anyway. So this and then the dynamical system of T on C is now our interest, but it is well-known method to analyze the behavior. That is so-called symbolic dynamics. So let S be the set of each element of S is an infinite sequence of 0 and 1, 0 or 1. And for each element X of the Cantor middle subset, let alpha X, that is an element of S defined by as follows. So alpha X is anyway is an infinite sequence of alpha 1x, alpha 2x, alpha 3x, dot, dot. And each of alpha ix is 0 or 1 defined as follows. So alpha so alpha ix I is 0 or 1 defined as follows. So this actually so let me explain this by this figure. So I mean, so this so let me consider the first alpha 1x. Alpha 1x is 0 if t so since I is 1, t0 x is x. So x is in the left part. So 0. So this is 0 to 1/3, and right part is 2 2 over 3 and 2, 1. So left half is 0 and right half is 1. And okay, so if alpha 2x is so this is so this part is mapped by t to this and this. So if we tx is left hand part, so this is 0, 0. So this is alpha 1x and alpha 2x. So this is alpha 1x. Alpha 2x is 1 because if x is here, then fx is sorry, tx goes to this right half, and so is 1. And this goes to 1, 1. So this one is already decided by this one. So you see, this one is because this is mapped by t to this interval, but the orientation is reversed, and this goes to this side. So this one is 0. And you see, this goes to this, 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 and this is goes to this. So this order is reversed, but these four, these 4 goes to these 4. So these 4 goes to these 4 in turn. So we see, for example, so this part is the third number corresponding to x in here is 1, because if we map x, tx is here and t twice x is here, and is the right half of the Cantor middle third set. So it is 1. So this is 1. In such a way, so by repeatedly apply this process, we have for each element, since x is in a Cantor middle third set, it belongs to some in any step, some closed interval. So then for x, in such a way, we can associate an infinite sequence of 0 or 1, like this. And we can see that that correspondence from Cantor set to the symbol of 0 and 1. Infinite sequence of symbols of 0 and 1 is bijection. So 1 to 1 and on to. So then let S be a shift map, meaning element of S is an infinite sequence of 0 and 1, and just delete the first one and shift A2 be the first and A3 be the next, like this. So this is called the shift map. Then it is known that action of T on the Cantor set is coherent to the action of S as a shift map. So this is a commutative diagram. So this direction is alpha. So you can see. So by this construction, I mean, for example, x is here, then fx, tx is here. So then just simply forget first 0, and then so for this x, some infinite sequence, the first 3 is 0, 1, 1, and something, and but the tx, the first 2 is 1 and something. So in such a way, we can easily check this proportion. And then, okay, now I'll explain how to prove the theorem. The theorem is so this one. So the theorem, the proof is still by example. So let F is a finite set of knot types. So the toroid and figure and 2, 5 torus knot. In the knot table, is 5, 1. So 3, 1, 4, 1, 5, 1. And we have some infinite sequence of these 3 knots. So here, the first one is toroid, the second one is figure and something. Some infinite, something follows. And then we so we again we take some connected sum method. So this is a toroid, but these part are annotated, also annotated. But take a diagram of figure knot and 2, 5 torus knot. So 3, 1, 4, 1, 5, 1. But these two are annotated now. And put so this is xy plane projection, and the important is the g level. And so put this red part is level 3/4, and put this under arc, so green part, so is level 0. So we see by t 0 and this is 3/4. These two are fixed points. So we see these crossing are fixed under the iteration of t. And the important is these crossing p, q, r, s. And then so this is p part. So if the sequence is first toroid and other knot and toroid again, then so we corresponding to this we take so this g1 level g1 the corresponding infinite sequence of 1 and 0 to be 1, 0, 0, 1. So this corresponds 1 is toroid and no toroid, 1, 0, 0, 1, and the under arc is to be the complementary one. So 0, 1, 1, 0. And then we can see, so this 1 means is 1 is one corresponds to the right half, and 0 corresponds to left half. And so for z coordinate, 1 is greater than 0. So this is crossing, and 0, 1 means if we map t, then the crossing change occurs. And next still this means still this is party crossing change, but this 1, 0 means it is again crossing change. So in such a way, for this p we take such sequence, and similarly for q and these levels are important, but we can arrange so this part. So that this is very sensitive. That to be the level of this part is should be precisely the x that correspond to such infinite sequence. Then anyway, we can, otherwise we have some errors when t goes to the iteration is goes to higher. Anyway, in such a way we can show we can prove the theorem. There are some questions. Is that construction should be okay? This. So this is the list. I'm not sure whether or not we can remove the condition of this finite subset. Okay, now I think it's time to stop my talk. Thank you very much.